This afternoon, I'll be switching gears, right, and talk about another feature in CompuCell3D that you can use, and which is the use of links or spring forces between cells and spaces in the medium. So this module 6.2 is actually one very big module divided in many small ones. Okay, so there is not really a division between part one and part two. It's more a continuous break into small parts. So we're gonna do the first two sub-modules here, see how it goes, and if I think it's time for us to take a break, we'll take a break maybe a little bit later or behind or before the time. But there's a lot to cover here. So this is a tool that is being used a lot. Okay. And actually there's so much use this that some of this you only be seeing tomorrow with Prion Adepak, when you actually combine the use of links and internal compartments of the cells. Okay. So basically, we are adding a spring force between cell center of masses, so you can link two cells or up to many cells, and that can lead to lot of all sort of active behavior. The cells actually pulling one another instead of just moving and kind of contact each other by adhesion forces or pushing other by growth, right? These actually cells directly pulling on each other and driving morphogenesis. So using a lot in some ways of morphogenetic processes. But before we start to go into the how it works, let's always, as always, start with the biology. And for this one, I like to really show this movie of conversion extension Zebrafish. And I want you to just take a look at this movie and see the cells, you see the nuclei, and take notice of all the movements and processes that are happening here. Okay, so I'll play that again. As you can see, you have a lot of process happening. First, you have the cells moving downwards, the process of epithelial. You see the cell division. You see the cells now converging and next toward the midline and extend along this line. You see the formation of the notochord right now. You see the more cells. What you see a lot here is many cells pulling each other, driving each other. It's not just growth, okay? It's patterning, is active pulling of the cells one another to make the pattern, to separate one another, to make a boundary. Okay, so there are and cells crawling in specific direction. Maybe don't see that in this video, but it's happening there. So all these movements you see development, yeah, many of them are active. It requires the cell to actually extend a force, either a pulling force, pulling other cell, or pushing other cell, or pulling the substrate to move itself forward. And maybe the cell that's moving is already linked with the cell behind, so it's dragging all those cells behind. So there are a lot of things that happens in development of tissues that requires maybe not only kind of passive addition of the cells, some kind of preference and contact, but actually the cells must be linked to extend to propagate those forces, or you can use those links to actually make the cell pull on each other or pull on the substrate. Okay, so all this to say that we need some kind of way for in CompuCell or cellular plots model to actually model this kind of force more explicitly, with more directionality, and maybe is a cell-cell type of force, pairwise interaction. Okay, And this is done in CompuCell3D through the use of links. So as I said that right here at the beginning, a link is basically a spring force, spring-like force, hooking force, like between two pair of cells. Okay, you start with that. And then basically you connect the center of mass of the cells. That's the point these links are anchored inside the cell. And then you can set a target volume, a target length, and a strength of interaction, and also some kind of distance at which the link breaks, okay? And you can make these links both passive or dynamic. You can make and create the links at the Python level, for example, okay? So, and then you do this for two cell pairs. You can do that. You can also do this for many cell pairs at the same time, as you see in the background figure here on the screen, and also in the snapshot here, where you have two cells interacting with one another. Okay. Okay, so examples of using the cell links. Okay, so already started with the view that's playing here from Dr. Abbas Shirinifar, where he used the links to model the a strong adhesion between the cell layer. And at some point, because you have this blood vessel trying to go in, it can break these strong links between the cells. Okay, that probably is mediated by the intermediate filaments inside the cell, which are connected to one another through the desmosomes. And once it breaks, then the blood vessel can break to this barrier, invade, and leads to the retinal detachment, as we see here. So that's an example where you don't see the links, but the links are there and drive the process. Another one that you have already seen before is we start with the epithelium that we developed in the last module, the stable epithelium. And then what you do, which is not visible in this movie here, is you add links between the apical cell compartments, and you select a subset here of those links to actually decrease or increase its strength. So that causes a little bit of a kind of furrowing formation here. Okay. And here's another example of this of links. Again, both internally and external to the cells. And here is actually another simulation using cell compartments. What's going on here is that the cells are usually made of a single compartment, this blue compartment. Eventually, they become polarized into apical, basal, and central compartments. Apical in green, central in blue, and apical and basal in red. And then you add those links to actually make those apical basal compartment to kind of push from each other. So you can think of this as maybe being the microtubules, if the microtubules are mediating this elongation. And that causes the cells to become longer and longer and longer. And at the same time, you add some kind of apical constriction process on the apical side of the cells also connect each other side by side, the apical link, and then contract, and that causes the this side of the cell to be constricted, while the basal side of the cell not to be constricted, and this causes kind of preference wedge shape of the cell that sets up what the size of the dish should be. So all these processes are done through the use of links in CompuCell3D. So just a bit of motivation biology and look in the simulations to see how that plays out in real applications. And so this is going to be the plan of action today. So this module is divided into 5 sub-modules, right? I'm probably going to go through the first 2 here and then go to the last 3 after the break. Let's see how far we go. But the idea is first the overview of how links work, CompuCell3D. So now some simple exercises. Go very slowly for you to get used to exactly how it works, right? Then we're going to do cell sorting, cell mixing with links. Then module 6.2, we're going to show how you can control the links at the Python level, okay? And maybe you can use that to actually create a deep tissue cell crawling model with links, okay? Module 6.24, we're going to also create a cell crawling model but instead of linking cell to cells, we're going to link in the cell with the substrate. So in this case, we call our links anchors, okay? Because like you turn an anchor and then you pull yourself in. And if you have time, we're gonna end with model 6.2.5, actually model conversion extension movements with links in CompuCell3D. Okay, so let's now go to model 6.2.1 and model first do an overview of how links work in CompuCell3D. Okay, so you may have seen this word before, focal points plasticity links or FPP. Basically, that's the name of the plugin that we use to model those links, okay? And what it does is basically uh, it connects the center of mass of the two cells, okay, with a spring-like force. So in terms of, in energy terms, that looks like this equation here, where lambda is going to be the force of the spring between the two cell center of masses. D is going to be the current distance between those 2 points, right? And this D target is going to be the resting length of the spring. So if the 2 points are about the same distance as the target length, right? This difference here could be 0 and the link will be at rest. So there's no force being produced. If this link gets extended, the cells should move apart. So the link becomes bigger. So this distance becomes bigger than the target or the resting length of the link, then you generate a force, right? And restoring force in one direction. But if these two cells, for some reason, they become closer to each other, much closer than what they're supposed to be given this target length, then you also have a difference here, and you're creating a restoring force in the opposite direction that will drive the two cells apart. So you can use that to make sure that the cells stay at the same level they are, or if you depend on how much or what value you assign to target one that creates the cells to actually become closer than they would otherwise be, or be moved further away from what they otherwise would be. So we can create some kind of constriction of the tissue or some kind of extension of the tissue by just playing with this ideal target distance between the two cell pairs. So these rows here are the cell types or the cell, the two cells that we are connected to the links. So you can make the link very specific to the cell pair. So two cell pairs can have different value than the other cell pair or between different cell types. And of course, the distance between is going to be something that really depends on where the two cells are, and the target distance is something that you can also manipulate and say, okay, these two cell pairs will have a very short target distance, and these other two cell pairs are going to have a very long target distance. Or maybe this cell pair will have a very strong interaction, so you can make this lambda bigger, or these two cell pairs, they have a link, but they have a weak interaction, so you make this lambda smaller, okay? So this is the energy term, and again, this standard constraint, the actual distance between cell 1 and cell 2, and the target distance between cell 1 and cell 2. Okay, so basically that's how it works, right? So it's not that complicated. It's you only have two controlling terms, right? And then you may be asking, okay, how do I add this to my code? Well, if you are making your code anew from the wizard, right? What you have to make sure to have all this is make sure that you select focal point plasticity in a wizard. So when you come to the cell properties and behaviors panel, you select focal point plasticity, and it's gonna paste the code there ready for you in the XML for you to create the links between the cells. Okay. When you have focal point plasticity, it's also a good idea to select the cell neighbors in the property trackers. I think now is automatically selected. But when you're using this, it's very good idea to also have this one, because sometimes you also want to change those links properties at the Python level. And when you do that, it's going to be very convenient if you're also tracking who's the neighbor of whom, so you can take a cell, look over the neighbors, and connect a cell with one of the neighbors, right? So having the ability to do the cell neighboring loop is going to be very useful when you're dealing with links. Okay, so once you select this in your user and create your code, that's how the app links look like at the XML level, right? You'll get a new plugin name called FocalPointPlasticity, okay? And then you show this line of code, and let's walk through how exactly what each one of those terms means, okay? So first you can see the parameters. There's a list of parameters, and you have 5 parameters here that you can choose, okay? Let's start with the terms that you already know, have already seen before. This lambda here is just the strength of the link. So it's written here, this in red here. So strength of 10, 20, 30. If you make a strength of 0, you have that the same thing as deactivating the link. And the target distance that I said that's also important is set here. So in this case, the target is going to be 7 pixels or 7 voxels between the two center of masses. Okay. But you can also see that you also have other parameters here and other numbers and other names here. What do they mean? Okay, so these two are the most important ones. So the others are a little bit more auxiliary. So let's start with something that's not really a parameter, is that type 1 and type 2 here. What is type 1, type 2 is the cell type that you have. So if I define a cell of type my cell, right? And I only have one cell in to help in my simulation, it's going to only create one set of parameters for that cell pair. So I have cell my cell and cell 2 my cell. So that's all interaction between of those two cell types. Or the cell types will belong the same type, right? So that's same type cell interactions. So this could be your type cell A and cell B. So if you define a cell A and cell B, then what happens is that you're going to have 3 instances of this code here, right? AA, BB, and AB, each with its own set of parameters, okay? So each one can have its own lambda, own force, and each one can have its own target volume, target distance, right? So in this case, I'm just showing for one. I just create a simulation with one cell type. I call the cell type my cell, so we're going to only see my cell and my cell, okay? That's what it means. Now you also see something else. Let's start with this one. We have a parameter called maximum distance or max distance. So this uh, is in units of voxels or pixels, and it sets how long you can stretch your link before it breaks. Okay, so you have a target distance of 7, so the cells should be at 7 pixels apart from each other, more or less. And if you start to bring the cells close together, they're gonna uh, push away from each other. If you start to bring the two cells away from each other, there's going to be restoring force. And there is a limit of how much you can pull them back. If you start to stretch too much, a little bit more, then eventually, if they become a distance that is 20 pixels or more, this comment here tells that this beam is gonna break, right? And so basically the elastic broke, okay? And then you don't have, those two cells are not linked anymore. That's what it means. So at the distance at which the link breaks, okay? So if you make this distance very high, bigger than the size of your lattice, that means that the cells will always be linked and never break. If you make this distance very close to the target distance, that means that any small fluctuation away from the distance may be enough for the two cells to break the link. So they're going to be a very brittle kind of brink. You're not going to be very elastic, right? Any kind of deviation already breaks. Okay. You may want to have that, may not have. You want to have a lot of link remodeling. You make the start maximum distance very close to the target distance. So any small deviation already break the links, and then the cells can come together and make a link again. And these cells come together and form a new link is what explain these other terms, okay? Which is the activation energy and the NeighborOrder. But before I go there, let me just give one more example, say one more thing. you have this other parameter that's very important, which is called the maximum number of junctions, okay? And maximum number of junctions, and here you have the number 1. What does that mean? That means that for this cell, can only have up to one neighbor of the same type that's linked with each other, okay? So if I have a bunch of cells of type, my cell should have given this another name. So if you have a confluent tissue of cells, right? So each cell in 2D will have more or less 6 neighbors. So in principle, this cell can link with any one of those 6 neighbors, right? But if I set my maximum number of junctions to be 1, that means that the cell can only have one link with one of its neighbors and gonna ignore the other 5. So if I increase this to 2, 3, or 5, or 6, then I can have more, the cell link with other cells, so you have more spring force between the cell and its neighbor. So that controls how much junctions you allow that cell to have. In this case, it's only 1 for that cell type. If you have another cell type, you may have cell type A, and A will have a maximum junction of 1, but the cell type A and B can have number of maximum junctions of 3. So each cell of type A can have up to 1 other A type connected, but up to 3 type B cells connected. That's what it means, okay? A question for Kaya, how does it choose which junction to link in that case? Is the lowest energy bond? Well, that is a little bit more stochastic. As you do your lattice copy attempts, as you evolve the tissue, right? As soon as 2 cells interact from another, right? The first cell that the original cell interacts with is the cell that's going to create the link, okay? If it's allowed to, okay? So if there's some kind of pixel copy of cell A towards cell B, then you can try to make the link between them, okay? However, one thing that's where these other parameters come from, okay? So this neighbor order here says how close 2 cells have to be before they can create a link between each other. So as soon as one cell move, it get is gonna if you start interacting with the other cells, if it gets close by the and if it gets too close, okay. So in the if this neighboring order is very high, the cell doesn't need to actually touch the other cell before it can create the link. So if you have a neighbor order of 4 or 5 or 6, as soon as one cell gets close to another cell, you can already create the link. If you have a neighbor order 1, that means that the cell actually to touch the other one before it can create the link. So that's what this neighboring order means, okay? The other thing that have is that you have this activation energy. And the reason why you have this activation energy here is to make the creation of the links more favorable. Because basically when you create the link between 2 cells, okay, you're adding a new term to your cost energy function or your Hamiltonian, right? Every time you add a new term in the Hamiltonian, especially one that's quadratic, right, which can only be positive, you're basically increasing the energy of your system. So from an energetic point of view, creation of 2 links of a new link is always so expensive that's not favorable to do, okay? So if you just go by this criteria, you'll never create a link between those 2 cells, okay? So this activation energy, and you notice that's negative, is something that's applied on the creation of the new link so that it becomes energetically favorable for this link to be created. So that's what it comes from. So usually we set this to -50, and that's usually a good enough number. So we usually don't worry about that, okay? So we just create the link, and usually the links when they created, they're already very close to the resting, the cell distance already very close to the resting distance. So it's a little bit easier to create, but you add this negative activation when actually lower the barrier for the creation of the link. And after you use that, you don't use that anymore. And now it's going to be, the link's going to stay there forever until you reach the maximum distance, then the link breaks. Or you set a command from the Python level. Okay. So what's the auto neighbor for? Well, we have two. This one is a general one for all the parameters, but you can also specify a neighboring order for a specific pair. So you can break down to, so A and A, they have to be very close to each other to make a link, but between A and B, they can be further away and make the link. So this one overrides this one if they are different. So one's a global one that is going to be specific. Does it make sense? Okay, I know that it kind of sounded complicated, but don't worry. What you really have to worry about is these two parts that you set the lambda, the strength of the force, the target distance, and also the maximum distance and the maximum number of neighbors. So that's what you're going to be playing in this first part of the module now. Okay, so let's now do an exercise to create a model with links from scratch. Okay, so we're going to do this from scratch. You can follow with me like we did in the last module. If you don't want to code because you're maybe too slow, or you're too lazy, or you just prefer to hear what I'm saying first, you can just go to the folder and download 6.2.1, and you already have this part of the code already coded for you. Okay, but for the ones that want to go along, let's open Tweedit and let's create a new project, CompuCell3D project, new CompuCell3D project, and let's create a model with links from scratch. Okay. So first thing, let's give the name module 6_2 underscore links. Okay. And leave it Python plus XML. If you want, you can give another name. Okay. Let's leave everything as it is, like X, Y, and Z. Let's leave like that, leave rectangular slab, and just hit continue. So no modifications in the first panel of the simulation wizard. Now let's add your cell types. So here I gave the name my cell. Maybe you can give another name. Maybe your cell type should be AA or mesenchymal, or I don't know. Pick up your cell type, your favorite cell type, and add that there. That's going to be your cell type. Okay. Make sure that the cell type appears here before you hit continue. Okay. So hit add to appear there, and once it's on there, you hit continue. I think you already know this now. So then let's ignore the chemical fields. And the next one, remember what you have to do. We have to select, I think, contact and volume flex already select for you. And now center of mass, you have to make sure that you select focal point plasticity. Otherwise, we cannot do anything. Okay. So make sure you select this one. As I said before, it's a good idea to also select some neighbors. So for this exercise, you don't really need, but go ahead and select it as well. So once you do this, your configuration is complete. Congratulations. And then you can go tweet it, and you can already look at the code and see how it looks like. The question was, some name was not selected. Yeah, I think I did not select it here. So in this example they're going to work on is not really important. But go ahead and select this. Better to select that's something does not slow down your simulation by any amount. So yeah, 4.7 comes selected. But when I create this slide, it didn't, it was 4.5. Okay. So yeah, just leave it selected. That's the best thing to do. Okay, I think that everybody's done. There was nothing complicated here. So let's now, if you run simulation, you may be very frustrated because you don't see any links. Where are my links, right? If you don't see any links, that's because we did not ask the player to visualize. So now it's just kind of visualization things. If you want to see your links, just go to visualization and make sure that epic links is selected. You have the check mark there. Okay. If you have the check mark there, then you'll be able to see the links. And they usually are shown by default as white. Okay. Depending on what your configurations look like, your cell boundary colors may be also white. And then that may be a little bit complicated. Too much white on the screen. So what I like to do in my personal preference is to have the links to remain as white, but the cell boundaries to be black. Okay, so that's my personal preference. So if you select them to have different colors, then you'll be able to see the links more clearly. And I personally like to have the boundaries black and the links white. If you want to change the color of the boundaries, remember you have to go to click on the toolbox here on the player, which sits right here, and there you can then click on each one of those squares and change the color of the boundaries or the links. And also for exact, if you have your link's going to be white, you probably want to use a darker cell color. In this case, I use darker green because then it becomes more visible. Okay, you don't want to have a yellow cell and a white link unless you have really good eyes. Okay. All right. I think have everyone configured their colors accordingly. If you do so, you may realize, okay, that what the first thing you notice here in this figure. Do you get something that looks similar to my screen here? Except for the colors? What's the first thing you notice in terms of links? Are there links there? It's only one per cell pair, let's say. Each cell is only linked to one cell, right? Why is that? Which parameter controls that? Okay. So now if you understand why you have only one cell pair connected, yes, the subcells do not have links. For example, this one here is lonely. It has no pair. Okay. Okay. It's just because the creation of these links is random. It's not optimized for all the cells to have a pair, right? If you have an even number of cells, by definition, one cell has to be remain lonely, right? But because the creation of the links is random, whatever interacts with the other cell first, right? So let's continue here. So you may notice that the maximum number of junctions. So if you go to XML code, you see that this is exactly what you get by default. This is 7, this is 20. So all the numbers that I showed before actually are the default numbers that it creates for you. And you see that the default number for the maximum number of junctions is 1. So that's why all the cells have up to one junction. And as we notice, some cells remains single, right? Because they don't want to pair with any other cell, or they didn't have the chance to pair. So it's more like this case, okay? So now what you can do, you can do your first exercise. Why don't we change this number and make it bigger and bigger and bigger, right? And let's just change that. Do yourself and tell me if he's behaving as we expect. Okay, so let's do this now. So let's change this parameter to 2, 3, or 4 and see the effects. And it's something that you can do either in the code, you can go to the code and change the number of junctions and play it again, or it's something that you can also do on the player. If you go to the player, that's this model part there, you can expand the focal point plasticity, and then you can find the maximum number of junctions parameter, and you can change that to 2, 3, 4, okay? But I think if you do that on the player, you can only increase. If you decrease, you will not see an effect. But let's do that. Let's change the number of junctions and see what you get. Okay, there was a question about should you delete medium cell and medium parameters. Yes, it was not supposed to create those pairs because you cannot really link a cell with the medium. Okay, so if it's there, you can safely delete them. Do not worry. Okay. Now there was a very good question from Joanna. She noticed that besides these parameters, you also have another block here called internal parameters, right? So for this simulation, you can delete the internal parameters. You do not use them. Do you have any guess or when we use internal parameters? Exactly. Use them when you have compartments. Okay. So sometimes you want to link two cell types only when they are within the same compartment. And sometimes you want to link two cell pairs only if they belong to different cell compartments, right? So if you use compartments, now you have to specify wherever your link is between compartments that belong to the same cell or between compartments that belong to different cells, right? So that's why we have this duplication here. So when you're using links to compartments, now you have to worry about is this an internal compartment pair or an external compartment pair. Okay, so that's when the internal parameters comes from. Does that make sense? Okay, so we have our first picture from Joanna, and yes, but Joanna, don't say anything. I want to use your image to ask a question for the people. Please look at the image from Joanna. But look at this picture. Can you tell me what's the maximum number of junctions that she chose? Did Joanna chose 3, 2, 4, 5, 1? How do you know it's 3? Because you can see a cell with up to 3 junctions, right? So that's actually the maximum that you can have. So the maximum number of junctions is going to be the maximum. I mean, you see some cells with just 2 junctions. I didn't see any cell with only 1, but you never see a cell with 4 junctions, right? So most of them is either 2 or 3. So she probably used the 3. So is that true, Joanna? Did you use 3 on that figure? Yeah, it was 3, but now she show another one. Okay, how many junctions Joanna used on the last figure? How do you know it's 8, Taylor? 8 or more, right? She may have done 9, she may have done 10, but we don't see because maybe the cell didn't have it's hard for the cell to make more than 6 connections or 7 when it's tied into D, right? But you should have get the something similar, right? So yeah, Joan, he was then, but he won't find any with 10 to, yeah, it's gonna be hard. Uh, if it was a three-dimensional simulation, then you can go to 10 very easily, right? Uh, but in 2D, with all the cells with the same size, what you get 6, 7, maybe there's a fluctuation and you get 8. Uh, sometimes, as you see. But that's it. Okay, so let me show my next image. So you must have get something that looks like this. So this with 1, This with two links, and then when you use two, you get a lot of lines. So actually, that's a good way to create a maze, right? If you have three now, that's what you have seen with Joanna. Then four, five, and when you select six, basically every cell is connected to each other, except for the cells on the boundary. They cannot have six because they only see three or four. But every cell in the bulk see we have about six neighbors, right? So this is for you to see the how this parameter controls. So maybe one more cells, maybe one less cells. Okay. Karine also show her image, and that is three cells. There's one cell there that has only one link. Okay, so why this happens, Herini? It's probably uh, because the process of link formation is random, right? Maybe by the time that cell that want to create a new link with the one above it, the one above right had three links, and the one to the side the right had three links. The one below right have three links. The one to the other side had three links, and only the one to the top right had two links, so it was able to create one. But now when it tried to create the other ones, it cannot because it was just frustrated. Okay, so it always have this case by chance, right? That all the other cells had already used the maximum number of junctions. So even though that cell does not have reached its maximum number of junctions, all the neighbors have already reached it. So that cell just becomes frustrated, and you only made one link. Now let's go back to the to my slides. So here we play with the number of junctions. So now how about we play with the target distance, okay? Right now the target distance is 7 and the cells about 7 by 7 pixels. So when they make the link, the cells are very happy with the link. But what happens if you make it smaller? And what happens if you make it bigger, right? So let's try to do this change here. Now let's play with the target distance parameter, okay? And for this one, the best and the results are done if you change parameter directly on the player. Right. So make it smaller first and then make it bigger. Okay. And then tell me in the chat what happens when you make it smaller and what happens when you make it bigger. Very good questions from Anastasia. So how come when I load the demo, the player shows the same colors as developers and not my default play colors? Is that specified somewhere in the code? Uh, Not in the code, but it's specified somewhere. Inside your simulation files, there is a file called sklights. Light, I forgot the extension, but there is a file. Is a JSON type file which specifies the colors. Okay, so when you download the code from me, it already came with that file that specified the colors of the cells. So that's why your initial choice was overridden. Yes, underscore settings.sqlite. So that simulation has the colors. If you reselect the colors, play simulation and stop, you're going to reset that file. And now if you share your code with someone else, there's someone else who's going to inherit your colors. Okay. It used to be that you could specify the colors of the cells in the code, in the XML file code. But that's no longer the case. And since Maciek is here, I give my appeal to Maciek to restore that comment because I thought it was very useful. I prefer that way to specify in the code, but that's my preference. Okay, so you see already a figure from Joanna that looks very weird, very bizarre. Can anyone tell me what Joanna did there? Yes, Anastasia is correct. She probably increased the maximum distance of the cells. So yeah, that's what happens. So here So when you decrease the target distance, you start to compress the cells, right? A little bit. So that induces some kind of compaction of your whole tissue. And our tissue becomes harder to be deformed by external forces. So decrease target distance to be lower than the cell typical diameter makes the tissue to be more rigid, start to condense. Okay, if you decrease too much, however, what may happen is that you may start breaking the cells. Okay, because now the cells won't have a target distance between each other that's equal to 1 or 2, and the only way that it can happen because the cells have fixed volumes for one cell to kind of envelop the other, and so that's what happens in the last image that Joanna sent. You see that the center of the links are not necessarily coincide with the center of the cells. That's because the cells have broken into many pieces. Another center of mass lies somewhere else. So this is an artifact. This so that is an indication that you went too far. Okay. Uh, if you start to increase the target distance in the cells, then you start to have these effects here. Your stitch becomes a little bit more fluid-like. You start to have some kind of uh, weird deformations. Again, it's up to you to decide if this is something biologically realistic or not. Okay, but if you go too further away from maximum distance, you start to get in the results can be very dramatic. As I said here, you can start to have this kind of behaviors, like things kind of start spread out like this, and sometimes it breaks, right? If you make your target distance bigger than your maximum distance, then the cell's gonna push apart and break. Right, that's what's gonna happen. The cells should come together, they link each cell, they push apart and break. Uh, that may be that may be reflects some kind of real process that happens in biology. I don't know, but that's something that you can get. So we can always use the tools that we develop in CompuCell, right, to model things that are unrealistic, right? It's up to you to make a correct choices, right, to make it reasonable or unreasonable. Yeah, the problem is that when you decrease the maximum, so there was a question. If I decrease the maximum number of junctions in the player, I don't see an effect because the junction is already there. You cannot by just deleting that, you'll make sure that no new ones are going to be created, but the ones that have been created is already there. The criteria to delete them is not the maximum number of junctions. The criteria to delete them is whatever they exceed the distance. So that's why the maximum number of junctions you can use the player to increase, but you cannot use the player to decrease. Okay. So yeah, it's okay. It's because the removing of the junctions is by distance criteria. Maximum distance is the distance at which the links break. Okay. So if you take a regular simulation, decrease it to, let's say, 4 maximum junctions and make the target, the maximum junction to be 8 or 7.1, you can use real numbers, right? So target distance 7, maximum distance 7.1. What you see is the links are breaking and reforming all the time. Try to do that and see if you get this effect. So did anyone try to make the maximum distance very close to the target? Yes, you can try to also use periodic boundary conditions and then the link's gonna wrap around. Things become nice when you start to combine plugins, right? And combine functionalities, and then you can get whatever you want. Then there's unlimited things you can do with the simulation. Okay, links do not seem to change a lot with maximum number of junctions. One, but it does when you increase the number of junctions. That's when you make the target distance very close to the breaking distance. Yeah, I think so, because they're more likely to connect with the same cell, right? So then you expect the links to. So if we make maximum junctions of 3 or 4, then maybe you can see the link remodeling happening more often, right? So when you make those two numbers, target distance and maximum distance very close, that leads to a lot of link remodeling, right? And that may be something that you want to have. If you want to have the links and interaction to be very dynamic, that's what you do. If you want to make them to be very stable, you set the maximum distance to be very high, to 1,000 pixels, and then they never break. So let's move on. Let's start module 6.22, modeling cell sorting with links. So this time we're going to have two cell types, and we're going to add links between them. We're going to see how the code looks when you have more than one cell type in your simulation. Okay, so it's a little bit more complex exercise because you have two cell types. So let's create a simulation with links, but now we have two types of cells. They're going to, let's call them G and P, which is going to stand for green and purple, okay? So that's the names that I chose. So when you do this, okay, what you notice, so let's go back to the tweeted and let's create a new file, okay? So a new CompuCell3D project. Let's call it module 6_2_ sorting links, okay? And go to the wizards by yourselves and select as the cell types G and P, which stands for green and purple. Create your simulation, right? And see if you get a collection of green and purple cells as you see here. So I'll leave this as an exercise. And let me know when you finish creating that multiple from scratch. Yes, you need volume. So leave the cell volume, the cell contact, and the number of neighbor tracker. Don't forget to select focal point plasticity in your wizard. So basically we'll be doing the same thing as this, right? Create a new file. We're going to give a different name. We're going to say sorting links. That's one name that you can have. Leave this as it is. Here, instead of my cell, we add a cell called G, another cell called P, which is going to stand for green and purple, right? You can ignore the chemical fields. And here, make sure that focal point plasticity is selected. Otherwise, you don't get links. Okay. So how is everybody doing? I know that's one colleague. Now Fatima she already got it. Okay. So if you run this code successfully or create this code successfully, you might notice that in your focal point plasticity plugin, now you have 3 terms instead of 1, right? Or maybe 6 terms. At least 3 important ones. First, you have a set of parameters that controls the connection between green and green pairs, right? Another one that controls the green and purple pairs, and another one that controls the purple and purple pairs. Okay, so each one of those links is a different nature because a different pairwise interaction, right? So you can specify different parameters for each one of them. So it may have a different target distance between green and green. You may have a different maximum distance for the green and purple, or you can have a different interaction force between purple and purple than the other ones. So you should get this, and you have control now of each one of those pairs. You can treat each of them independently, right? You cannot treat using on the XML different cell pairs of the same types differently. If you want to do that, I mean, you have two green to be different from this green and the green on the right to be different. If you want to do that you have to do on the Python level, right? That's gonna something they're gonna look later. But on the XML level, you can only different the interaction between pairwise types of cells. Okay. Does it make sense that does everybody has a code that looks more or less like this, and when you run the code that looks as Fatima has shown in the screen? Please let me know, say yes in the chat. Don't say yes on your say in the chat, because there's too many people, I cannot see all of them at once. So if you do the thumbs up in your screen, I cannot see. Yeah, yep. Okay. So now that you have, so you can already see that if I define 3 cell types, they're going to have way more interactions, right? Then that goes to 7 types, right? And then that's all the combinations that you can have. Okay, no, I think 7 that you're gonna get. So the more cell types you have, the more pairs wise you have, and you have to specify each one of them. Okay. But now that you have 2 and those 3 kind of different set of parameters to play with, what you can do with those parameters. Okay. So I'll now propose 2 sets of exercises. Actually 3 exercises. So the first one, make one pair of cells to have very short links, and the other pair of cells have very longer links, and check what happens. So try to do this first, and select either green or purple to be the short one, and the other one to be the long one. Do that and see what that makes, how that looks like. So please do the first one and show in the chat a snapshot of our simulation. Once you have played that, then you can actually have these 2 challenges here, which is, can you get set those parameters in such a way that you can get cell type mixing, and can you change your parameters in such a way that you have actually cell sorting between the 2 populations. But let's first do this one. Let's change the parameters of the number of links or the length of links to be shorter and longer one, and see what happens. There's a question in the chat. There was automatic creation of a paragraph with type P and G and P. Is there a difference between both? No, there should not be a difference between the directionality of the links. Okay. When you use the Python code to create the links, you can specify one cell to be the initiator, the other one to be the receptor. That may be important for some cellular processes. But at the XML level, there is no difference between them. So you can delete one of them very safely. There's no problem. I don't think so it seems that the XML is generating more pairwise interaction than it should. For example, it's creating medium, and cells and medium. So if there's any CompuCell3D developers out there, that's something that we may want to take a look to not generate the cell pairs that never gets used. Okay. Oh yeah, it's a good idea to change NeighborOrder so you have more neighbors between cells. So I see that Joanna posts a picture. She made the purple cells to have very long links, and the green to have very short links. And not sure if you change the green purple links. I think you also change those. right? Yeah, but not as drastic as the green. So if you're done making very short links and very long links, and see that they affect different cell pairs, okay? What the challenge now is to try to reproduce the results of cell sorting and cell mixing with only links and do not change the adhesion parameters at all, okay? So now that's the cell mixing is easier to get. So try to change the what parameters you have to change to induce cell mixing to get that checkerboard pattern. I believe that in the beginning of the course last week, you did some simulation with cell sorting, right? To have one cell to go to the inside, to the outside. And you also have done simulation with cell mixing or the checkerboard pattern when you make the heterotypic addition between uh, cells of different types to be more favorable than homotypic additions, and then you get the checkerboard pattern. So the question is, can you get the checkerboard pattern with playing with only links? Okay, so let's try to do this one first, and place a picture. If you get it, something that kind of looks like a checkerboard pattern, please paste on the chat and tell us what you did. Maybe different recipes to get that. So it'll be nice if everybody try to participate and contribute. So let's try to get cell type mixing by just changing the parameters. How is everybody doing with the exercise? Did anyone get the cell mixing to happen? So what strategy are you trying to use to get mixing? A few of you got it, right? Okay. So remember, there's a tip there. If you make the maximum distance close to 7, right? Make 7.5 or 7. Or 8, we're gonna induce more link remodeling. Okay, so you probably want to have that. So that's gonna help you. Now it's better to set the maximum distance higher than the target distance. You make it lower, so you always break. So it better make the maximum distance always bigger than the target. Remember, you can also play with the strength. We didn't play with strength so far, so the lambda is also a factor that you can use. So what we're going to do now is going to share my recipe for the mixing, and then I'll leave the sorting as a next challenge. So here is how I got the mixing. So the cells are mixed with one another. We have more, the green and the purple are very mixed, okay? And the way that I did this by saying the following. First, I went more extreme. I set the maximum number of neighbors between green and purple to 0. Okay, so I don't want them to interact with links at all. Okay, so that when they do not interact. And I only change the green-purple interaction. I leave lambda equal 10, the target distance to be 1. So they are very pull themselves very strongly. And I kept the maximum number of neighbors to be 3. So when I use this set of parameters, I get a cell mixing that looks like this. So doing the sorting, the mixing, and the sorting of links a little bit more challenge. Is definitely more challenging than doing that with cell adhesion. Okay, it's possible, but it's not that of a good mechanism, right? So change the adhesion properties is more robust, is better, right? Use on links is it's a little bit harder, so that's why I say it's a challenge. Okay, but For the mixing part, if you use these parameters here, you should get something that very close to what I have here. Ah, Clara, you made your target this to be 100, super high. So that's where everything exploded, right? But the string should have broken because your maximum distance was 10. Yeah, I don't understand that, honestly. It should have broken. I do not know why it did not. Clara, you also said the maximum number of junctions to be 0. Not sure if that has an effect on that particular simulation. Please now try to get to have the cell sort, so the two tissue types separate. So the green to go to each other, and the purple to go each other. So we are minimizing now their interactions rather than maximizing what you have done on the left. So try to do the reverse of this. Oh, that's very good, Clara. Actually, that's better than what I got. What did you do to get this? Ah, okay, so you make a very big target distance and maximum distance of 20, so they push itself apart and break. And whenever they come into contact again, they push themselves apart and break again. Okay, so they're really kind of pushing each other. So that was the mechanism. And then we probably set the green and purple to actually condense. Kai also got it. Uh, Kaya, you got the mixing, but you also got the cells to break. Okay, so you got the desired effect, but notice that all the center of masses of the cells, uh, the link does not coincide the center mass of the cells because the cells probably broke into many pieces. So you had cell fragmentation. So on this one, you probably set the target distance to be very small. Like you said, target distance to be very small and also the lambda very strong, right? You probably did both things. So you usually don't want the cells to break. So notice that I did use a very low target distance, in this case 1, but my lambda was not that high, so you don't see the cells breaking to 2. So you can use a very short target distance that cells really pull each other, but then you have to be careful of not at the same time use a very strong lambda because you can need the cell breakage. But what probably what Kaya did, she was inducing condensation of the different cells. Okay. Rocio, I can see that you make the interaction between purple and green only, and you do not allow for any interaction between purple and green. So that's a very different strategy than Clara used. So Clara had a very strong interaction of purple and green, but a repulsive one. Now we have a neutral interaction with them, but mm, I think you can push that a little bit further. Actually, you use the same strategy that I use. Okay. And I can also tell that's the same strategy that your other colleague used. So I do not know how to pronounce your name, is like, but basically have no links between those two different cell types. Like, okay. All right, so it's already 2:30, which is actually the time for this module, if I'm not mistaken. Uh, so I'll share now the strategy that I used. Okay, so is this one here. Um, So what I said here, I set the maximum number of neighbors of green and purple to be 0, which means so they'll never interact with links. And I set the green and the purple to be slightly different from one another, okay? And so both of them, you have a small target distance and a maximum distance of 7, so they can, because the cells are 7 by 7, right, can tend to be stay more or less at that distance with one another. So a target distance of 7 actually is very close to the breaking point. So you have lots of cell remodeling, okay? The target distance is 1 on both, so it is very condensive. And the difference between the green and the purple is that the green is more, it condenses more than the purple. Okay. We see that the lambda of the green is 15 is stronger, so a strong interaction. And also, I also allow for more interactions, up to 6 neighbors. While for the purple, the string of interactions lower, it's 10, and allow for lower number of interactions. The idea here was to attempt to have some kind of engulfment of the green over the, sorry, the purple over the green. So I kind of got this, a little bit of this. You see that there's more purple going the outside and less and more green going to the inside. But again, you can do some kind of cell sorting, and this time I was actually doing cell engulfment. I got a little bit, but not that much. So when you're trying to reproduce the cell sorting, cell engulfment of one type from the other, it's better to use cell adhesion. Cell links you can get only so far, okay? But that was my recipe, and you see that other people have done other recipes, and that's the nice thing, because a group of modelers to try to produce a process, and each one will come with a slightly different recipe, right? Which probably reflects not that one is wrong, the other is right, probably because in biology there are multiple ways to achieve the same result, right? So it can be by this way, it can be another way, right? So maybe for a specific system there's a correct result, but in generally, what drives cell sorting? There are many ways and many mechanisms that drive cell sorting. Even use the same kind of basic mechanism. For example, here, using the interaction links, right? You can have multiple recipes that are going to result in the same endpoint, okay? So if you want to have a copy of those files that implement those 2 strategies that I shown here, you can download that. There was a question, how do you get a checkerboard? The checkerboard I did by using this strategy here, where I have no interaction between green and purple, and a condensing interaction between green and purple. So that's how I get the checkerboard. Of course, it's not a perfect checkerboard, but it is something that goes in that direction, okay? And again, using the addition energies, you can get these outputs better, right, more efficiently. But the idea of these 2 first modules to get you is to get you familiar of how links work, what you can do with them, and what we're gonna do in the next modules after the break. We're gonna use them from the Python level to see what you can do from the Python, how you can modify on a cell basis, right? So we start the next module by trying to model cell crawling, okay? We maybe also do cell crawling with anchors, and if you have time, you can even try to do cell conversion extension with links, okay? But that's going to be for after the break. I will just give you a sneak peek for you to stay along. I'm going to stop here and let either Hayden or James run the course module questionnaire.
So for following tomorrow's tutorial, I think also TJ's one is probably best if you can have VSC, Visual Studio Code, installed on your computer, and that will help you to follow along. It's not required, obviously, but is one way more. So I thought I would assemble this slide to have a quick reference. These are pretty straightforward, but there might be sometimes issues. And so if you need, just drop a line to me or anybody else in the group, and we'll try to address those.